Hi everyone, we are PT7 and we'll be presenting on the dry-bean dataset. So this is our contribution table. So dry beans are an economically important global crop and the seed quality directly affects the agricultural yield, the pricing, as well as the overall market value. However, the traditional manual sorting methods are very time-consuming and inconsistent, especially because many of the bean varieties look very similar in shape and structure. So to address this, we'll be using machine learning models to automatically classify the dry beans into 7 different categories using their geometric features such as area, perimeter, as well as compactness. So the dataset that we'll be using is the UCI dry bean dataset, which has about 13,000 samples with 16 numerical geometric features extracted using image processing techniques. So this is a supervised multi-class classification problem where the models are trained to predict the bean type along with a probability score. So for our design rationale, the first thing that we observe is that there's a large variation in feature scales. So for example, the feature area has values in the tens of thousands, while other features has values closer to 0. So without scaling, the features with larger magnitudes could dominate the learning process. So one of the models we'll be using later is logistic regression, and this is very sensitive to scale because it learns weights using optimization, and if some features have much larger values than others, then they can dominate the learning process and make the training very unstable and affect the decision boundary. And in addition, regularization may penalize the features unfairly if they're not properly scaled, so this can reduce the model performance, which is why we apply standard scaler to ensure that all the features contribute equally. Also, we realized that the dataset exhibits class imbalance. For example, the Dermison class has significantly more samples than the Bombay class. So if we rely solely on accuracy, then the model could achieve very high performance simply by favoring the majority classes. So to address this, we evaluate the models using additional metrics such as the precision, recall, as well as macro F1 score to provide a more balanced assessment across all the classes. And we also use stratified sampling to preserve the class proportions in both the training and test sets, and this ensures that minority classes such as Bombay are still being represented.
We applied principal component analysis (PCA) to reduce dimensionality and remove redundancy caused by strong multicollinearity observed in the coloration matrix. PCA transforms the original features into a smaller set of components while preserving 95% of the total variance, so we kept most of the important information. This helped improves stability for models like logistic regressions and k-nearest neighbor, which are sensitive to correlated features and also makes it easier to visualize class separabilities in lower dimension. For our model selection, we started with logistic regression as our baseline model. This is a linear classifier, which means it tries to separate the beans type using straight lines in feature space. We choose this first to check whether the bean classes can already be separated using simple linear boundaries. If this works well, it means the problem is relatively simple. If not, then we know we need more complex models. Next, we use k-nearest neighbor KNN since our dataset contains many numerical measurements like size and shapes. We wanted to see if the bean that looks similar naturally groups together. KNN classifies a bean based on the majority class of its nearest neighbor. So if similar bean clusters together, this model should perform well. After that, we move on to the random forest. For our exploratory analysis, we observe that many features are highly correlated. Random forest is suitable here because it can handle correlated features well and does not assume linear relationships. By combining multiple decision trees, it can capture more complex patterns and potentially improve accuracy. Finally, we tested a multi-layer perceptron, which is a neural network model. Since the relationship between bean features and bean type may not be simple, we wanted to see if the neural network can learn deeper and more complex patterns that simpler models might miss. This allows us to compare traditional machine learning methods with a higher capacity model.
For our experimental setup, we are using Google Colabs. For data management, we use Pandas and NumPy to load, clean, and transform the data. During exploration data analysis, we use Matplotlib and Seaborn to visualize features and class imbalance. For the machine learning framework, we use skip learning. It will allow us to build structured pipeline that integrate pre-processing steps like scaling and PCA together with the model training. This ensures that pre-processing is applied, consistent, and avoid data leakage. Finally, we split the dataset to 80% training and 20% test. So our training configuration for pre-processing, we apply standard scaler to normalize the feature scaling. Scaling is actually important for a distance-based model like KNN and for gradient-based model like logistic regression and MLP. You also apply PCA retaining 95% of the total variance. This reduces the dimension from 16 features to 4 principal components. PCA was not applied to random forests. Next, our comparator for four models was we set max tier to 5000. This ensures the algorithm convert properly especially after dimension reduction. For k and n, we select 5 neighbors. For this balance bias and variance, a smaller k may overfit, while a larger k may oversmooth decision boundaries. For MLP models, we use two hidden layers with 64 and 32 neutrons. We also use RU activation because it improves training efficiency and reduce vanishing gradient issue. To prevent overfitting in MLP, we apply L2 regulation with alpha equals and enable early stopping. Early stopping monitors validation performance and stop training if no improvement is observed over 20 iteration. Using 10% of the training data as validation, this helps improve generalization. For our random forest, we set random state to 42.
For our evaluation framework, we use multi-matrix because our bin classes are imbalanced. With Sierra being much larger than Bombay, we prioritize the F1 score. This ensures that every bin is treated with equal importance to prevent the model from cheating. We wanted to ensure that our model actually learned the unique characteristics of every bin, regardless of how many samples were in the dataset. We also track average confidence. It acts as a reliability check and tells us if the model is making decisions based on shown patterns or just guessing. Our analysis method utilized the confusion matrix to isolate specific miscalculation pairs, and after that we cross-reference with our PCA variance data. We didn't just look at total error, we analyzed the top confusion pairs to find the root cause. This allowed us to prove that our metrics were being dragged down by features dominance in shape and sizes, especially affecting the Sierra and Thomason classes, because these bins are almost identical. The drop in matrix shows features limitation than a model fault. We noticed our top performer, Random Forest, had a perfect 1.0 training score, but a 0.92 test score. This shows that the model has reached an information ceiling. It essentially memorizing training samples to try and overcome the overlaps in the data. By analyzing the variance, we identified that the root cause of the size and shape that dominates 82% of the dataset. This proved that no matter the model complexity, we are limited by the similarity of the bins.
So let's talk about the result and error analysis. Based from this table that we created of all four models that we use, random forest is the best model to use. It has the highest accuracy, macro matrix, highest average confidence, and near perfect training accuracy. But there's a generalization risk to monitor. Followed by second, MLP. It captures non-linear interactions but needs hyperparameter tuning to be close to random forest. For KNN, performs similarly to logistic regression in accuracy but has a high reported confidence, which is a sign of overconfidence. Logistic regression is our interpretable baseline, as is the worst performer. It underperforms where feature interactions matter. Now let's move on to the database. For Bombay, it's essentially soft, a clear unique signature in its features, thus is being easily classified. For Dermison, it performs well in aggregate, but exchanges many errors with Syrah. Because Dermison is the largest class, even small relatively errors can create absolute misclassification. Syrah, being the largest total source of errors, it overlaps with Dermison and being the top operational issue. Horos and Seeker are highly reliable. It is high in precision, high in recall, and only minor boundary confusions. For Kelly, most separatable, but receives some issues with Banunia, implying a size overlap, and Banunia, being the worst, has actually improved substantially under Random Forest, but has small residual confusions with Kelly. So now let's talk about the error failures and plausible causes. For feature dominance, most variants are in shapes and sizes, so classes that differ only by fine textures get confused. For class overlap, such as Syrah, Dermison, and Banunia and Kelly, inspect misclassified samples and relabel where necessary. For model capacity, random forest models non-linear boundaries well. For logistic regression, it underfits. KNN is sensitive to scaling and noise, and MLP requires hyperparameter tuning to work. For overfitting risk, random forest will show a training and test gap, so regularize its trees, validate its stratified K4 and OOB. For scaling impact, because Syrah is large, improving its recall by a few percentage points will reduce the total misclassification.
Now, I will briefly explain the limitations of our project and the proposed improvement. First, one limitation is overfitting in complex models. Our random forests achieve very high training accuracy, but slightly lower testing accuracy. This suggests that the model may have learned patterns specific to the training data, which limits its ability to generalize to unseen data. Second, our evaluation relied on a single stratified train test split. Although stratification preserves class distributions, the result may still depend on a chosen random seed, which reduces the reliability of the evaluation. Third, we applied principal component analysis to reduce dimensionality. While PCA preserved 95% of the dataset variance, it transformed original features into abstract components. This reduced interpretability and may have removed some useful class-specific information. Fourth, feature overlap between similar classes was observed. Several beans varieties have very similar size and shape characteristics, which led to consistent misclassification between certain class pairs. Finally, our models had limited hyperparameter optimization. Most models were trained using default or near default setting, which may have prevented them from achieving their best possible performance. Based on these limitations, we propose several improvements. First, we recommend using stratified k-fold cross-validations. This would provide more stable and reliable performance estimates by reducing dependence on a single data split. Second, we suggest systematic hyperparameter tuning using grid search or random search. This can help optimize model settings and improve accuracy and fairness across classes. Third, stronger regularization techniques can be applied. For example, limiting tree depth and regularizing neural network can reduce overfitting and improve generalization. Fourth, targeted feature engineering can be performed. By developing ratio-based and interaction features, we can better distinguish between frequently confused classes. Finally, we can explore advanced classification models, such as support vector machine SVM and gradient boosting, which may further improve performance on structured numerical data. In conclusion, this project successfully developed and evaluated multiple machine learning models for dry bean classification. Through systematic pre-processing, dimensionality reduction, and comparative analysis, we found that ensemble methods achieve the strongest overall performance. Although limitations such as overfitting, feature overlap, and limited tuning were identified, practical improvements have been proposed to enhance robustness and generalization. Overall, our results demonstrate the effectiveness of machine learning for agriculture data and provide a clear direction for future optimization. Thank you.